So, as we discussed in our previous video, we basically defined what is a grand canonical partition function means by like this, right? Theta of zvt is equal to sum over nr is equal to 0 to infinity z raised to nr qn vt. So this is how we define the grand canonical partition function. Now let's apply this in one single situation, which is ideal gas. Ideal gas using grand canonical ensemble. So in this point, it is important for you to remind yourself our derivations which we have performed for an ideal gas in the 3-dimensional and the 2-dimensional situations. So remind yourself that those points. So we have theta equal to sum over rs e raised to minus beta es e raised to minus alpha nr equal to sum over rs e raised to minus beta es e raised to mu nr beta, right? And then based on this we have written the our expression, this expression, right? So now in order to apply this equation, we should write down what is a partition function for an ideal gas in the basically 3-dimensional ideal gas in the canonical ensemble situation. So therefore, if you go back in your notebook, so Q of nr is equal to V by lambda cube raised to n divided by 1 by n factorial. So this is how we have defined the term over there, right? So we will substitute that for, instead of n you can always put the nr over here. There's no harm in that. Since we are going to do the integration over nr, so let's put nr instead of n, because we are going to do the summation over there. So therefore I substitute that. So theta is equal to sum over r v by lambda cube raised to nr 1 by nr factorial into z raised to nr, right, which I can simplify as sum over r z v by lambda cube raised to nr into 1 by nr factorial. So this is how I can do it. But based on one of the mathematical expressions, I know that sum over x raised to n by n factorial is equal to e raised to x. Right? This is one of the mathematical identities which we know. Sum over x raised to n by n factorial is equal to e raised to x. So therefore, if I apply this, e raised to x expression, I can write down theta is equal to exponential ZV by lambda cube, right? Because our x, this is our x raised to n, this is nr factorial. So therefore, this is the expression. Theta is equal to exponential ZV by lambda cube. So that is it. So basically, we have now calculated ideal gas, three-dimensional ideal gas partition function. With the same kind of idea, you can try yourself the systems like 2D ideal gas and all those things. So this is one of the method in which you can derive the partition function, the grand canonical partition function for a typical system. But only thing is that we should have the correct kind of mathematical identities in place so that we can simplify this expression and read something like this. So if I take the if we need to calculate all the other thermodynamic parameters, like we need to have the A, right? The Helmholtz free energy. A is equal to kT ln theta. So we have derived already how can A is equal to kT of ln of partition function, right? In our canonical ensemble derivations. So we simply apply that, replacing it with theta over here. So kT ln theta, which if I apply that over there, and this, if I apply this theta over here, I will get kT ZV by lambda cube. So A is equal to kT ZV by lambda cube, right? And then definitely you should try to derive the other set of normal thermodynamic parameters using this information of the A and this theta also. Okay, so you should definitely try to do that. I am not trying to do over here in this video. Okay.